Intermolecular forces. Now, the term intermolecular means the connection or the attraction between atoms. It's like an interstate freeway, connects states. Intermolecular forces bond together molecules. Now, we've learned that molecules can be polar. Well, that polarity attracts molecules to one another. Again, it's referred to as an intermolecular force. Now, the covalent bonds that we've been looking at can be called intramolecular, the attraction between atoms within a molecule. Now, don't confuse that with our new topic here. This is the attraction between molecules. So, intermolecular force, a weak attractive force that exists between molecules. So here's ammonia. The dashed lines here represent this force of attraction. Again, don't confuse that with the covalent bonds of within the molecule itself. When a molecular compound melts or boils, intermolecular forces are being broken, not the covalent bonds. So if I was to melt ammonia, it's not the covalent bonds, it's the intermolecular forces between the two. For water, when you melt water, you're breaking the bonds between the water molecules. Okay, there are three types of intermolecular forces. Let's look at the most common of all dipole-dipole forces. An attraction between polar molecules. By the way, polar molecules are referred to as dipoles. We talked about bond dipoles the other day. When we're talking about just a dipole, it's just another name for a polar molecule. So if a molecule is polar, it can also be called a dipole. So here we have two dipoles, two polar molecules, and of course the positive part of one molecule will have an attraction for the negative part of another molecule. And so that's our dipole-dipole force of attraction. As an example, hydrogen chloride. Chlorine is more electronegative than hydrogen, and so this is an uneven sharing of electrons. It's a polar molecule. The positive hydrogen will be attracted to the negative chlorine of another molecule, but that's a completely different bonding. That's just an attractive force. The dash here is a sharing of electrons. The half-filled s orbital is overlapping with one of the half-filled p orbitals of chlorine. Very strong covalent bond. This very weak, just an attraction for. Next, dispersion forces, or London dispersion forces. London is a scientist. It's not named after the city. The weakest intermolecular force resulting from shifting of electrons from one side of a molecule to another. Example, iodine.
An iodine molecule has, on average, an electron cloud that is symmetrically spread over each iodine atom. I2 is not polar. The attractions or repulsions between the atoms of I2 molecules can distort their electron clouds. Dipoles can thereby be induced momentarily in neighboring molecules.
So you have these very weak dipoles of simply as a result of the electrons moving around within the molecule itself. The larger the molecule, the greater the dispersion forces, because the more electrons you have. Occurs between all molecules, but it's the only force between non-polar molecules. So when we look at the attraction force between non-polar molecules, the only force is dispersion forces. But all molecules have electrons moving around, so all molecules have dispersion forces. It's just that for other molecules, for polar molecules, dispersion forces are so weak compared to the dipole-dipole forces that they're usually just ignored. We're going to watch a little video now on how do geckos defy gravity.
It's midnight, and all is still, except for the soft skittering of a gecko hunting a spider. Geckos seem to defy gravity, scaling vertical surfaces and walking upside down without claws, adhesive goos, or superpowered spider webs. Instead, they take advantage of a simple principle. that positive and negative charges attract. That attraction binds together compounds like table salt, which is made of positively charged sodium ions stuck to negatively charged chloride ions. But a gecko's feet aren't charged, and neither are the surfaces they're walking on. So, what makes them stick? The answer lies in a clever combination of intermolecular forces and structural engineering. All the elements in the periodic table have a different affinity for electrons. Elements like oxygen and fluorine really want electrons, while elements like hydrogen and lithium don't attract them as strongly. In atom's relative greed for electrons, it's called its electronegativity. Electrons are moving around all the time and can easily relocate to wherever they're wanted most. So when there are atoms with different electronegativities in the same molecule, the molecule's cloud of electrons gets pulled towards the more electronegative atom. That creates a thin spot in the electron cloud where positive charge from the atomic nuclei shines through, as well as a negatively charged lump of electrons somewhere else. So the molecule itself isn't charged, but it does have positively and negatively charged patches. These patchy charges can attract neighboring molecules to each other. They'll line up so that the positive spots on one are next to the negative spots on the other. There doesn't even have to be a strongly electronegative atom to create these attractive forces. Electrons are always on the move, and sometimes they pile up temporarily in one spot. That flicker of charge is enough to attract molecules to each other. Such interactions between uncharged molecules are called van der Waals forces.
Dispersion
They're not
forces.
as strong as the interactions between charged particles.
Van der Waals forces is a term that IB no longer uses. We just use dispersion forces.
If you have enough of them, they can really add up. That's the gecko's secret. Gecko toes are padded with flexible ridges. Those ridges are covered in tiny hair-like structures, much thinner than human hair, called setae. And each of the setae is covered in even tinier bristles called spatulae. Their tiny spatula-like shape is perfect for what the gecko needs them to do: stick and release on command. When the gecko unfurls its flexible toes onto the ceiling, the spatulae hit at the perfect angle for the van der Waals force to engage. The spatulae flatten, creating lots of surface area for their positively and negatively charged patches to find complementary patches on the ceiling. Each spatula only contributes a minuscule amount of that van der Waals stickiness. But a gecko has about 2 billion of them, creating enough combined force to support its weight. In fact, the whole gecko could dangle from a single one of its toes. That super stickiness can be broken, though, by changing the angle just a little bit. So, the gecko can peel its foot back off, scurrying towards a meal or away from a predator. This strategy, using a forest of specially shaped bristles to maximize the van der Waals forces between ordinary molecules, has inspired man-made materials designed to imitate the gecko's amazing adhesive ability. Artificial versions aren't as strong as gecko toes quite yet, but they're good enough to allow a full-grown man to climb 25 feet up a glass wall. In fact, our gecko's prey is also using van der Waals forces to stick to the ceiling. So the gecko peels up its toes and the chase is back on.
Pretty cool, huh? Okay, now let's look at the effect of van der Waals forces on the noble gases. This is a chart of the boiling point of noble gases. Of course, the boiling points are very low temperatures, but if they were all cooled off to the point that they were frozen and you began to warm it up, first helium would melt, and then neon, and then argon, krypton, xenon, radon. And why would that be? Well, let's just look at helium and argon. So you have dispersion forces between helium atoms. Now, don't confuse this with diatomic. Again, the dotted lines here are just an attractive force. Helium only has 2 electrons, so those 2 electrons are moving around here. And so if you have more of those electrons on one side, it's going to be partially negative on that side. So it's a very weak intermolecular force with helium with only 2 electrons. Argon has 18 electrons, and so it's going to have more dispersion forces between the atoms. And so that's why argon has a higher boiling point than helium, simply because it has more electrons. As you go down the family, the melting and boiling point increases because the atoms get larger. Weak dispersion forces, stronger dispersion forces. Key idea, key takeaway here, the larger an atom or molecule, the greater the dispersion force, and therefore the higher the melting point or the boiling point. And last, hydrogen bonds. A stronger dipole-dipole attraction between molecules that have hydrogen bonded to nitrogen, oxygen, or fluorine. You might remember from the last notes or last unit, we talked about nitrogen, oxygen, and fluorine being the three most electronegative elements. So when we look at the bond that hydrogen would form between those three elements, it's particularly polar. It's a very, very polar bond. So therefore, hydrogen, when it forms an attractive force between another molecule, is particularly positive. And so it's going to form it's still a dipole-dipole force of attraction. It's given a special name, hydrogen bonds, because it occurs when hydrogen is bonded to one of these three elements. Now it's important you don't confuse the covalent bond between hydrogen and the atom in the molecule. It's just that that bond is so particularly polar because nitrogen, oxygen, and fluorine are so electronegative that hydrogen's kind of holding on for its dear life, almost exposing its proton. Remember, hydrogen is just one electron and one proton. So if the one electron it's sharing is mostly over on this side, it almost has its proton exposed. Not quite, but you kind of look at it that way. So it's a particularly strong bond. There is no distinction between a hydrogen bond and a dipole-dipole bond. It's exactly the same idea. It's just because it's so much stronger than a typical dipole-dipole bond, it's given a special name. Now, when you're asked to name the bond, don't say hydrogen. Hydrogen is an element. The name of the bond is hydrogen bonds. It's an example, water. The dotted lines there represents the hydrogen bonds between water molecules. So this is water in the liquid state, and that is in the solid state. You can see that when it's in its solid state, let me kind of do it going backwards. So this is water in its liquid state, and the molecules are actually closer together. When it begins to freeze, the molecules rotate around and maximize the number of hydrogen bonds between the molecules, forming what we call ice crystals. When water melts, it's simply melting, it's simply breaking the hydrogen bonds. Now, liquid water still has hydrogen bonds, just not as many. Hydrogen bonds are very important in biology. If you've had IB Bio, you undoubtedly have talked about hydrogen bonds. For example, when we talk about the double helix of DNA, the two strands on the either side are linked together by hydrogen bonds. That's what it's kind of like a twisted ladder. The rungs in the ladder that holds the two sides together is hydrogen bonds. Now, hydrogen bonds are very weak, but there's so many of them that it keeps it together. Okay, looking at relative strength. Now, covalent bonds are in a category all of them their own. So covalent bonds are much, much, much stronger. And I say that over and over again because students will, one of the most troubling answers on a test is when they rank a hydrogen bonds dispersion forces or dipole-dipole forces as being stronger than covalent bonds. Covalent bonds are light years away from the very, very weak intermolecular force between atoms. Maybe I overstated that, but trying to make the point. Okay, so covalent bonds are strong, and as we go down here, the next would be hydrogen bonds, again, much weaker than covalent bonds, and then dipole-dipole forces, and then the weakest of all, dispersion forces. Now, in order to determine whether the molecule is going to have what type of intermolecular force it'll have, we simply need to ask a couple of questions. So first, is the molecule polar or nonpolar? Well, if it's nonpolar, as we talked about earlier, the force of attraction would simply be dispersion forces. But if it's polar, it could be either dipole-dipole or hydrogen bonds. So ask the question, are there any hydrogen fluorine, hydrogen oxygen, or hydrogen nitrogen bonds in the molecule? If no, then it's a typical dipole, and it's dipole-dipole forces between the molecules. But if yes, then that molecule will hydrogen bond with another molecule. Looking at increasing strength, and that would be also increasing melting point or boiling point, dispersion forces would be the weakest, then dipole-dipole, then hydrogen bonds. Now that's what you need in order to answer the last couple of columns on your molecular shapes lab. You need to determine if it's a polar molecule, it's either going to have dipole-dipole forces or hydrogen bonds. If it's nonpolar, it'll be dispersion forces. Dispersion forces would be low melting point, hydrogen bonds would be higher melting point, and dipole-dipole would be in between. Okay, that is it. End of our notes.